Welcome to Chemistry 111. Today we're going to continue looking through some of the homework, continuing with the stoichiometry homework. We're coming to the last week or so of school, so I will be sending out the test maybe later today. It's not going to be due till next week, but you want to make sure if you got the time to go ahead and do it, because not long after that is going to be the final. Quick reminder, since we're Monday, Wednesday, Friday, I do believe our final is on Wednesday. Gotta double check. It's either Wednesday at noon. I'll be able to get back to you later about the exact date, but I know it's definitely the coming Wednesday. We're going to have some study sessions in the library where the SMACS members are going to be trying to, and I will probably be trying to help. I think we're going to do one 11th. There's plans for another one on the 15th and the 16th, so you're more than welcome to show up. Maybe there's extra credit in it. I don't know. We'll see. But either way, that's a chance to help review for the upcoming final, maybe review for the test, may get some help if you need some help. Okay, so let's go on and continue with this. So the answers are already revealed because I did this problem yesterday and I forgot to clear the answers, but we'll still work through it. So work through it because the whole idea of what I'm trying to do here is show you the process. So if you can use the same process to solve your problem. This is part of a percent yield question. Percent yield is essentially, we're going to do grams to moles to moles to grams. And then we're going to apply the percent yield equation. Percent yield equation is percent equals actual, which is the measured amount, over theoretical, or you could say it's calculated, whichever, times 100. That's our basic equation for this. So almost all percent yield problems will start with you're given an actual quantity and a starting reagent quantity, which you can use to calculate your percent. So reading this question, excess of oxygen reacts with 451.4 grams of lead, thus forming 353.7 grams of lead oxide. Calculate the percent yield. So real quick, what have they given us? They've given us the amount of lead, so 451.7 grams lead. And they've given us, 451.4 grams lead and 353.7 grams of 353.7 grams of lead oxide. So in order to solve this, we need to calculate how much lead oxide would be formed. So we're going to go to grams of lead to moles of lead to moles of lead oxide to grams of lead oxide. It just so happens, since I did this problem yesterday, I remember a bit of this. Looking up on the periodic table, we would get the molar mass of lead is 207.2 grams of lead per 1 mole of lead. So grams of lead cancel grams of lead. Now we have 2 moles of lead for every 2 moles of lead oxide. So a 1-to-1 ratio cancels out our lead. We're left with lead oxide. So the last step is to convert this to lead oxide. So 1 mole of lead oxide, what is the molar mass? 207 plus 16 puts us at 223.2 grams of lead oxide. Moles of lead oxide cancels moles of lead oxide. So if you have this is the second to last problem on stoichiometry, the assessment A. So if you have this problem, you might have a different mass of lead, or you might have a different mass of lead oxide. But if you have this equation with the lead, you set this up the same way. So 451.4 1.4 0.4 divided by 207.2 times 2 over 2, which is the same number, times 223.2. You'd get how much lead oxide should you get theoretically? What is the maximum amount possible? The maximum amount possible would be 486.3. So putting that in, 486.3 grams of lead oxide. At that point, all we have to do is divide those two numbers and multiply by 1,000. 46.3. And that's where we get my 72.7. So, as I said, I've already solved this yesterday for my Tuesday, Thursday class. But that is the generalized process. The next question, which is the last question on this set, crap. All the way back to the beginning. Let's see. Okay, good. Last question is similar, except instead of calculating your percent yield, you're given a percent yield and asked to calculate the actual yield. Now, while I will not ask you to do that on the test, we can still do that just fine. We still have the same percent yield equation. So, reading this question, assuming efficiency of 29.6, so percent yield of 29.6, calculate your actual yield of magnesium nitrate formed if I have 114.1 grams of magnesium and excess copper. So plug in what we know. We have 29.6 here. So we want to go from 114.1 grams of magnesium to grams of magnesium nitrate. With that in mind. So we look up the mole. We're going to go grams to moles to moles to grams. Going to keep doing that. That's the whole point of this chapter. Grams to moles to moles to grams. Or, as you're going to see in the next set of homework, molarity to moles to grams, or molarity to moles to molarity. But we're always going through moles. Now, looking up periodic, the mass of magnesium, it's 24.3 grams of magnesium for 1 mole of magnesium. So now, for every 1 magnesium, we get 1 magnesium nitrate based on the balanced chemical equation. So 1-to-1 ratio, that makes this easy. Grams cancel grams, moles cancel moles. So what is the molar mass of magnesium nitrate? This is the only thing that could be a little bit of a challenge. So, as I said, magnesium is 24.3. Each nitrogen is 14. There's 2 nitrogens. Each oxygen is 16. There is 6 oxygens because there are 2 nitrate molecules per magnesium. So the total molar mass of this guy is 148.3 grams of magnesium nitrate. So with that in mind, we're going to convert. So 114 divided by 24 times by 148.3. So what is the theoretical yield of magnesium nitrate? You should get 696.3, at least on mine. As I said, if you have a different mass, you're going to have to plug a different mass in there. You cannot just copy this number down, but the setup should be the same so long as you're dealing with magnesium. As long as you're dealing with the same problem, you should maybe just have different number, maybe a different chemical equation. Double check and make sure you're dealing with as close a problem as you can. Now, how do I solve the last bit? We have to isolate the actual. So to do that, we're going to divide both sides by 100. So that's going to make 29.6 into 0.296. And multiply both sides by the 696.3. And that will get rid of that. So you'll get the actual yield would have to be 206.1. Now, depending on where you rounded, you might have got a slightly different number. So 206 is good enough. But that was the percent yield problems for this chapter. Just want to quickly look at those. So we have gone over some example problems of that. Now I'm going to open up the assessment part B, which is the stoichiometry of molar solutions. Assuming this will open up. Depending on how we do, I might just end up recording me going through the test, doing that separately, and leave questions for Monday. Okay. So a lot of these, some of these are just calculating molarity. Some of these are going to be turning grams into molarity. Some of these are going to be dilution problems. Okay. Now this one is pretty darn simple. Molarity is solved by moles over volume. So this first guy literally is setting up 6.87 moles divided by 4.1 liters. Moles per liter would give us our molarity. Your numbers, as I said, may not be 6.87, may not be 4.1, but it should be something pretty darn similar. I get a molarity 1.68. So looking at the next problem. Okay. This one is just rearranging what it's asking for. So not really any harder. At least it shouldn't be. what we are dealing with here is, okay, now we have moles and a molarity, and we're solving for the volume. Moles, molarity, we're going to solve for the volume. Just need to put this on real quick. And it needs to be in milliliters. You got to check that. But so, rearranging my molarity equation to give us volume means we're going to rearrange that. So volume in liters equals moles over molarity. So if I'm dividing 0.0496 moles, 0.496 moles by the molarity, which is 0.18 molar, I'm dividing it by 0.18 moles per 1 liter. As I do that, it would give me an answer in liters. So the last step you would have to take is make sure to convert into milliliters, which, remember, in 1 liter, there is 1,000 milliliters. So times by 1,000, thus giving us 275, we'll say 6 milliliters. So that's just rearranging. These first two should not be a problem. Now, I'm going to skip this one because the first one is straightforward. The second one is a little bit harder, but the second one here is just like this problem 4. Problem number 4 asks us to go one step further. We are not just solving for molarity, we're now solving for molarity starting from grams. So, sodium hydroxide is extremely soluble in water. They give us, at a certain temperature, 531 grams of sodium hydroxide is soluble per liter. So what they're giving us is a ratio of 531 grams of NaOH per 1 liter. They're giving us a ratio of grams per liter, and we're expected to turn this into moles per liter. So what do we got to do? We got to divide by the molar mass of sodium hydroxide. Sodium is 23, oxygen is 16, hydrogen is 1. That is 40 grams per 1 mole. So 431 divided by 40 gives us a crazy concentrated solution of 13.275. It's really concentrated. It's dangerously concentrated. Okay. But so we can turn grams to moles to molarity, or moles to moles. Okay, so there's a first dilution one. So a dilution problem works under the concept that in a dilution, the moles of our molecule does not change. When we add more water, we are not subtracting or adding HCl molecules. We are leaving the amount of HCl in there constant. So what we're going to say is that if molarity times volume equals moles, and moles do not change, this is also equal to a molarity times another volume. So essentially M1 V1 equals M2 V2. So saying I have a 6 molar HCl and it's 65 mils, what is the concentration when we've diluted this to a final volume of 750 mils? So with that in mind, we will isolate the molarity. How do we do that? We multiply those two together and divide both sides by 750. So 6 times 65 divided by 750 gives us 0.52. 0.52. Now, this only works in a 1-to-1 ratio where the moles do not change. This one is much harder than what we will see on any sort of test because this one is not a 1-to-1 ratio. This one is a 2-to-1 ratio. In the following equation, 2 nitric acids neutralize 1 barium hydroxide. If 0.105 liter sample of nitric acid is required to neutralize 48.5 milliliters of 0.2 molar barium hydroxide, what is the concentration of nitric acid? So what do we got to do? We got to turn molarity of barium hydroxide to moles. Moles of barium hydroxide to moles of nitric, then moles to molarity. So we're breaking it down into those 3 steps. You can do it all in one equation. You can do it in multiple equations, but just take it as you will. So there is 0.2 moles of BaOH2 per 1 liter. Ba. We have to multiply by the volume in liters, so 0.0485 liters. So those cancel out. Now, here's where this is harder than usual. For every 1 mole BaOH2, we'd get 2 moles of nitric acid. And then we're going to divide by our volume of nitric acid. Volume of nitric acid to give us our concentration of nitric acid. So 0.2 times 0.0485 times 2 divided by 0.105. So the answer is, at least in my situation, is 0.185. Now I want to look, let's see, we'll come back to this one in a second. I just want to jump to this one real quick. No, not that one. The last one. The last one is closer to what we would expect for the exam. By titrating, a titration has found that 94.3 mils of 0.192 molar solution of sodium hydroxide is needed to neutralize 25 mils of HCl. Calculate the concentration of HCl. This is a standard M1V1 equals M2V2. It is a 1-to-1 ratio. It is not supposed to be hard. This one is similar to the lab we did, the titration lab. If you want to look at what you might be expected for the test, be able to do the calculations involved in the titration lab. That is more along the lines of what you should be able to expect. So try this one on your own. Okay, I'll work through these last two. These last 2 ones are a little bit harder, which I'm going to go ahead and do them. So a solution of sodium chloride is slowly added to lead nitrate until no further precipitation occurs. The precipitate is filtered, dried, and weighed. A total of 13.19 grams of lead chloride is obtained from a 200 ml solution. So what is the molarity of lead nitrate? So the equation, you don't need to know the equation, is 2 sodium chloride plus 1 lead nitrate goes to 2 sodium nitrates and 1 lead chloride. Because we're only going from 1 lead nitrate to 1 lead chloride. We're having an excess of sodium chloride. But we're starting with a massive product, and we're trying to calculate molarity of original solution, assuming complete reaction. So we're going to turn grams of lead chloride to moles of lead chloride. There's a 1-to-1 ratio of moles of lead chloride to moles of lead nitrate. And then finally, we're going to turn moles of lead nitrate to molarity of lead nitrate using the volume. So let's look at that. As I said, your mass of lead chloride may be different from my mass of lead chloride, so you can't just copy the answer, but you can set it up just the same. 13.19 grams of lead chloride. So the molar mass of lead chloride, remember we said lead was 207.2. Each chloride is about 35.45, and there's 2 of them. So the molar mass of lead chloride is about 278.1 grams per 1 mole lead chloride. Now, I'm going to kind of wave my hands a little bit, but there's 1 mole of lead chloride or 1 mole of lead nitrate. Technically, we have to do that, but it's 1-to-1. You kind of get lazy at times. Finally, in order to get molarity, I have to take my moles of lead nitrate and divide by our volume and liters. So 0.200 liters. So I'm going to take my 13, divide 13.19, divide by my pretty heavy molar mass, divide my volume, and I get the original molarity would be something like 0.237. Like 0.237. So remember, I turned grams to moles, and then I used the moles over volume to give me molarity. Now this one is a beast. We're going to go ahead and work through this one. This will take us a little bit of a while. So please try to pay attention. This is mess of one. I've left it on here because I already worked it out. Work it out again. Be an advantage you'll have over everyone else who's not watching this or not paying attention. So this puts all the concepts of this chapter together, all except for maybe percent yield. So a 155 ml solution of 3.185 molar strontium nitrate is mixed with 200 mils of 0.3692 solution sodium fluoride. Calculate the mass of the resulting strontium fluoride precipitate. So it's a limiting reagent problem. And then they want us to calculate the concentrations of each ion. The limiting reagent ion will be 0. Everything else, the spectator ions, will just be diluted. The non-limiting reagent, non-spectator ion, has to be subtracted out, which is going to make that one a really big pain. But first things first, what is the chemical reaction? Strontium is +2. So we have strontium nitrate, and fluoride is -1. So sodium fluoride will all go to sodium nitrate and strontium fluoride. So because of that, we have to double the sodium nitrate. So the balanced chemical reaction looks like that. Now, we want to calculate, let's calculate the moles of sodium, the moles of nitrate, the moles of strontium, the moles of fluoride. This is going to make my life easier in the long run. I know it doesn't seem like why are we doing that now. We'll do that now. So how do we calculate the moles? Moles are, remember, just molarity times volume gives us moles. And then, of course, times whatever coefficient. So, for example, strontium, probably the easiest. 3.185 times 0.155. Since it's molarity times volume. So 3.185 times 0.155 liters gives us 0.493675 moles. Now, I could almost copy that down for nitrate, but for every one strontium, there will be 2 nitrates. For every one strontium, there will be 2 nitrates. So moles of strontium times 2. So if I multiply that by 2, I'll get there is 0.98735 moles of nitrate. Now to calculate sodium and calculate fluoride, I'm going to take my molar mass, which is 3.69, or sorry, our molarity, 3.692, times by my volume, which is 0.2 liters. So 3.692 times 0.2, that's going to give us 0.7384. 0.7384. Okay, so we got the moles of each ion. Now we want to figure out the limiting reagent. We need, it's either going to be strontium or fluorine. Now you may be thinking, well, strontium has a larger moles, so strontium has a lower moles, so fluorine would be in excess. But we need to look at our balanced chemical equation. So for every 1 strontium, we need 2 fluorines. For every 1 strontium ion, we need 2 fluoride ions. So how many fluorine do we need to fully react with the strontium? Well, that's going to be equal to the nitrate. So nitrate, you would need 0.98735 moles of fluoride to completely react with my strontium. So which is our limiting reagent? It's actually fluoride. So let's calculate how much strontium fluoride could we generate. So from there, we're going to divide by 2 moles of fluoride per 1 mole of strontium fluoride. And then we have to look up what is the molar mass of strontium fluoride to figure out what that's going to be. So fluorine is 19, if I remember right. Fluorine is 19. Strontium is, that's the one I don't remember. Strontium is 87.6 plus 19 times 2. So the molar mass of strontium fluoride is 125.6. So the first question it asks is, how much strontium fluoride could be produced? The answer is we could produce what the heck happened? Okay, sorry. We could produce 4.637 grams. 4.637. Okay. Now, that should have been the easy part, and I know you're thinking, well, easy, that seems actually rather difficult, and that's true. Which should tell you something about the next part. The next part asks us, with that in mind, how much of all the ions are remaining? The guy that runs out the answer is 0. So we just said fluoride is the limiting reagent, so that one's by nature 0. So that's the easy one. Sodium and nitrate are spectator ions. So their moles will not change as the reaction progresses. So we just need to figure out what is the molarity of these guys. Well, we have their moles, but we do not have the molarity because what happened? When I added my strontium nitrate to sodium fluoride, what happened to the volume? It increased. I added 155 milliliters onto 200 milliliters, which makes this total 355 milliliters. So with that in mind, to calculate the molarity of nitrate, I'm going to take the moles, 98735, divided by our volume, 0.355. So the moles of nitrate, 0.98735 divided by 0.355 gives us the molarity of nitrate being 2.78. Doing the same thing with sodium. Taking my 0.7384 divided by 0.355 would give us the molarity of sodium being 2.08. Okay. Now, the strontium right here is the last part. It is the hardest part because we have to consume some quantity of strontium. We have to consume the amount of quantity that gets used up and then do the dilution. So breaking that out. First thing we got to do is we're calculating how much strontium reacted with that much fluoride. Then we're subtracting that moles out. And then finally, we are doing the dilution. So breaking that down, how much strontium do we need? How much strontium do we need? Well, how much strontium would react with the fluoride? So we had 0.384 moles of fluorine. We had 0.7384 moles of fluorine. And for every 2 moles of fluorine, we react with 1 mole of strontium. So how much strontium would react? We would react with 0.3692. Reacts. So how much strontium would be left if I removed 0.3692? You would get 0.124475 moles left. So I calculate this divided by 2. That gives us my 0.3692. Now we have that much left, and I'm going to divide that by 0.355, which is my total volume, to give you a molarity, the final molarity of strontium ions, 0.351. Now, keep in mind, that's a hard one. It really is hard. What? No. Where did I go wrong? Clearly screwed up the math somehow. Okay, let's see. Let's see what I did. 3 divided by 2. 6. Oh, that's a trick. Figured it out. That's not 4.6 grams. That's 46.37 grams. Honest mistake. Honest mistake. Yeah. Lost a decimal somewhere. But okay. So that is all. I mean, we might as well go through the last problem. We have the time. We'll go ahead and do that. But the last problem compared to that guy is nothing. It's literally nothing at all. So last problem is a standard 1-to-1 molar dilution or molar titration. Just like we did in lab. The moles of acid equal the moles of base at equivalence point. So if we know the moles of acid and we know the moles of base, we can figure this out. So if they say 94.3 mils of 0.12 molar base, 94.3 times 0.192 equals molarity times 25. We are solving for molarity. Just like we did in lab. We titrate the acid with the base. We figure out what is the concentration. So I take 94.3 times 0.192, divide by my 25, and I get 0.724. 0.724. Now, in lab, what did we do? Before we did that, before we titrated, we actually diluted by a factor of 5. So if we were to add that step into there, it would be 0.724 times 5 after it's all said and done. But this one, there's no dilution step, so that's all you need to do. Now, okay. But that is the stoichiometry homework. So I will probably at some point make some videos about working through some of the test problems, seeing as how next week is the week right before finals week. I want to be able to review all the material and not just this material. I want to be able to refresh you on all the stuff. So after this, we're going to go through some of the, after this, I'm going to post some extra videos about doing the old test, and we'll start reviewing for the old stuff. Next week in lab, turn things in if you haven't already. Come in, bring homework. We'll work through homework. It's a chance to make up any labs you need to make up. It's a chance to get help with your homework. If you don't show up, That's fine. Just make sure you've turned in everything you need to turn in. So, with that in mind, we have review days next Wednesday at 7 in the tutoring center or by there, and I think the 15th and the 16th. So at the same time in the tutoring center. But that's where we're going to stop for today. We're out of time. I'm going to work on the test and show you that later. Okay. Have a good day.